Welcome back to the Deep Dive, where we take your curiosity and transform it into crystal clear understanding. Today, we're plunging into a world where cameras don't just passively capture light. They think, adapting their vision on a pixel by pixel basis. Imagine a world where every single tiny dot that makes up your image isn't just a fixed receiver of light, but an active, intelligent sensor adjusting its gaze in real time. That's the revolutionary concept we're talking about today. Our mission for this deep dive is to unpack an incredible piece of engineering, a closed-loop, all-electronic pixel-wise adaptive imaging system for high-dynamic range videography. This isn't just about making your smartphone photos look a little better, It's about giving the eyes of advanced computer vision systems, think robotics, sophisticated security systems, and especially autonomous driving, an unprecedented ability to truly see the world as it is, without the frustrating compromises we've kind of come to expect from traditional cameras. We're looking at some cutting-edge research, specifically a paper titled A Closed-Loop, All-Electronic Pixel-Wise Adaptive Imaging System for High Dynamic Range Videography by Ji Zhang and colleagues. It's a fascinating read, and we're going to break down exactly what makes this technology a potential game changer for you and for the future of machine vision.
What's truly profound here is how this system fundamentally rethinks the very act of capturing light. I mean, really rethinks it. Traditional cameras, by their very design, operate with a global mindset. That means they make these broad compromises across an entire scene.
Right.
This research, however, moves us towards a truly local, intelligent capture at the most granular level. If we consider the broader impact, this could fundamentally revolutionize how machines interpret their environment, and perhaps even more crucially, how they make critical decisions based on that richer, more accurate information.
Many of us have likely experienced the frustration. You try to take a picture or video, and either the bright parts are completely washed out, or the dark parts are just a murky, featureless mess, or maybe something moving quickly just blurs into oblivion. What's actually going on behind the scenes with our standard cameras that leads to these common, everyday frustrations?
You've absolutely hit on the core issue that the researchers are trying to solve here. Most modern image sensors, the eyes of virtually all computer vision systems, really, from your smartphone camera to a complex security network or an autonomous vehicle, use what's called a frame-based architecture with global exposure.
Okay, global exposure.
Right. This means that every single pixel across the entire sensor array is exposed to light and then subsequently read out at the exact same time using the exact same exposure settings. It's a design choice that certainly makes manufacturing simpler and more efficient, no doubt. It allows for smaller pixels and better sensitivity under, let's say, ideal uniform lighting. But as you pointed out, it's inherently rigid in its operation. It's fundamentally a one-size-fits-all approach. And this simplicity, while valuable for production and basic image capture, creates significant problems in complex real-world scenes. Imagine a scenario with both blinding sunlight and deep shadows, or maybe a fast-moving object against a static background.
Yeah, happens all the time.
Exactly. A camera forced to use a single global exposure setting has to make a compromise. It tries to find some kind of middle ground that inevitably fails to capture optimal detail in either the bright extremes or the dark areas. You end up with either blown-out highlights or crushed shadows because no single setting can perfectly capture both simultaneously.
So it's almost like trying to light an entire stadium for a broadcast with just one master switch.
Precisely. Yeah, when some areas are in broad daylight, others in deep shadow, and maybe some players are moving incredibly fast across the field all at once.
Right, you just can't get it all perfectly right simultaneously with one fixed setting. That's the challenge, right?
Exactly. And this inability to adapt locally leads directly to the issues you described, which are frustrating for us as photographers, sure, but can be catastrophic for machines. The paper provides some really striking examples of this, particularly in their Figure 1. It vividly illustrates how this rigid global control creates problems when you have those large variations in brightness and motion that are, so common in our visual world. You clearly see instances of what's called local motion blur, where, for example, a fast-moving car in dim light would appear as just a streaky, indistinct shape because the global shutter isn't fast enough to freeze that motion.
Okay, yeah, I've definitely seen that.
And other examples in the figure show parts of the image that are completely black, totally underexposed. All detail and information in those areas are just lost. At the same time, other parts are pure white or blown out, indicating they're overexposed, and any information there is saturated and irretrievable. The paper specifically highlights how a globally optimized exposure setting always leads to this loss of critical information in either the saturated or the blurred regions. It's a fundamental trade-off. Wow. And this isn't just about aesthetics for your, social media photos.
Right.
For critical real-time applications like robotics, sophisticated security surveillance, or especially autonomous driving, losing this kind of visual information is catastrophic. If a self-driving car can't accurately detect a traffic light because it's completely overexposed by the sun, or if it can't discern a pedestrian crossing the street due to motion blur, well, that's a serious and potentially life-threatening problem.
Absolutely.
Errors in the initial image capture don't just stay in the image, they propagate. They ripple through to subsequent computer vision tasks, messing up things like motion estimation, object segmentation, even recognition. The machines quite literally can't see properly, leading to flawed decision-making.
So the core problem is clear. Standard cameras, despite all their advancements, are making these fundamental compromises that lead to critical information loss, which is a huge deal, especially for AI-driven vision systems that rely so heavily on accurate data. But this isn't a new challenge, is it? Surely engineers and researchers have tried to fix this before. What have they attempted, and why haven't those solutions truly stuck or become, ubiquitous?
Absolutely, you're right. This isn't some new revelation. Many attempts have been made over the years to enhance dynamic range and reduce these imaging imperfections. But as the paper points out, each of these prior solutions came with its own set of pretty significant trade-offs. They often added complexity, increased cost, or sacrificed other crucial aspects of image quality and speed that are vital for real-time video applications. The paper actually provides a great summary of these previous works, outlining their mechanisms and, importantly, their limitations. One common approach has been temporally varying exposure. This method is quite intuitive, actually. A conventional image sensor captures multiple images of the same scene sequentially, but at different global exposures. You'd take a short exposure for the bright parts and a longer one for the dark parts.
Like HDR on my phone, it takes a few quick shots.
Exactly like that, yeah. These separate snapshots are then merged using what are called tone mapping algorithms to create a single high dynamic range, or HDR, image. But the significant problem with this, however, is that it causes ghosting artifacts in non-stationary scenes.
Ghosting.
Yeah, if anything moves, even slightly, between those sequential snapshots, say a person walking or a leaf blowing in the wind, you get these blurry, phantom-like duplicates of the moving objects in the final image.
I see. Not good for video.
Definitely not. This inherently limits the effective frame rate, making it largely unsuitable for capturing smooth, real-time video. Then you have solutions involving multiple image sensors. To kind of extend that temporally varying approach to video, some systems use optical beam splitters.
Beam splitters. Like prisms.
Sort of, yeah. They send copies of a scene to several detectors simultaneously, with each detector set at a different exposure. While this does produce HDR frames in real time, it requires multiple cameras, which makes the whole system bulky and mechanically complex. It also demands extremely precise optical alignment, which is difficult to manufacture and maintain reliably.
And probably expensive.
Very. And crucially, splitting the incoming light means that each individual sensor receives less light. It directly attenuates or weakens the collected light, which degrades the signal-to-noise ratio, the SNR, at each detector. So you're sacrificing fundamental image quality in one aspect, noise performance, to gain dynamic range in another. A trade-off again.
So it's a workaround that adds a lot of physical complexity and potentially introduces more noise.
Okay. What about techniques that try to control the light before it even hits the sensor?
Right, that brings us to spatially varying transmittance. This approach uses external or off-chip spatial light modulators, SLMs, placed directly in front of the image sensor.
SLMs, what are those? Think of them like tiny, localized, programmable sunglasses, almost like a mini LCD screen controlling light transmission. They modulate the incoming light intensity at each pixel group. By placing such an optical mask across the focal plane, it can allow local pixel groups to capture a wider dynamic range. The main problem here, though, is that it requires spatial low-pass filtering to generate the final HDR image, which inevitably leads to a loss of spatial resolution. You often end up with an overall blurrier image.
So less detail.
Exactly. Plus, it adds the significant complexity of these off-chip SLMs that must be perfectly aligned to individual pixels, a huge and costly manufacturing challenge. Finally, researchers have explored adaptive optical light intensity modulation. This is similar to spatially varying transmittance but adds a feedback loop. These adaptive systems detect overexposed or poorly illuminated regions and then adjust the incident light intensity at those pixel-level regions to optimize the dynamic range. While it does improve dynamic range without sacrificing spatial resolution like the previous method, it still relies on those external, well-aligned off-chip optics.
Still need the extra hardware.
Still need the extra hardware. And here's another critical limitation. The underlying image sensor's frame rate remains fixed. This means it can't adaptively extend exposure to improve SNR when needed in darker areas. It's an optical workaround rather than an inherent integrated capability of the sensor itself.
This is truly a pivotal shift in thinking then. It sounds like all these past attempts were either adding bulky, complex external hardware, making things slower and causing ghosting, or losing resolution and sacrificing other vital image qualities. They were essentially trying to solve the problem around the sensor with these external, bolt-on mechanisms rather than tackling the core issue within the sensor itself, like putting a sophisticated Band-Aid on the wound rather than healing it from within.
Precisely. That's a perfect analogy. And this brings us right to the fundamental question that Zhang and colleagues implicitly asked. Can we achieve this pixel-wise adaptation without any external optical modulators? Can we make it an inherent all-electronic capability directly at the pixel level? That's where they made their significant breakthrough, moving towards an integrated solution that handles these issues at the most fundamental point, the pixel itself.
So if the previous solutions were like bolting on extra features to a conventional camera, this new system sounds like it was designed from the ground up for truly intelligent vision. Tell us, how does this pixel-wise adaptive imaging system actually work? What's the core innovation that makes it so fundamentally different and, well, potentially so much more effective?
This is where our deep dive truly begins, getting into the elegance of their design. The system described in the paper is a beautifully integrated solution that achieves pixel-wise exposure control without any external optical modulation whatsoever. It's essentially an electronic feedback loop that happens at an incredibly granular level for every single pixel in the camera. The overall architecture, as illustrated in Figure 2 of the paper, consists of three main parts that work in concert. At its heart, of course, is the unique image sensor itself, which boasts this pixel-wise exposure configurability. This is the eye that can adjust how each tiny part of it sees.
Okay.
Then, acting as the system's vital nervous system is a high-speed, bidirectional chip-to-computer interface. For prototyping, they implemented this using a PCI bus, which you might know from your computer for high-speed graphics cards.
Right, yeah.
And finally, orchestrating all of this, the true brain of the operation is the real-time exposure controller, which, for this prototype, was implemented off-chip on a computer.
Got it. Sensor, interface, controller.
Exactly. These three elements work together in a continuous closed-loop operation. Think of it like this. The image sensor captures a frame, let's say at time t1, and in that frame, a bright sky region appears completely overexposed. This raw data is immediately sent via that PCIe interface to the exposure controller. The controller then acts like an intelligent processor. It rapidly analyzes this data, segments regions of suboptimal exposure, identifying precisely which pixels are too bright, too dark, or perhaps blurred. Then, critically, it recalculates the desired exposure settings for each individual pixel based on that analysis.
For every single one.
For every single one. These updated, optimized exposure settings are then fed back to the image sensor with incredible speed. The sensor, in turn, updates its configuration for each pixel based on these new instructions. When it then samples the very next frame at time 2, both the previously overexposed sky region and all the other regions of the scene are optimally sampled. It's a continuous cycle of sensing, analyzing, and adapting, all happening in real time, potentially hundreds of times per second, depending on the setup.
That's incredible.
What's also notable is their vision for the future. The paper explicitly states that the PCIe link and the external exposure controller, which are currently off-chip for prototyping purposes, can be integrated into a single system on chip, or SO.
Ah, like putting the brain right onto the sensor chip.
Exactly. And SACO is like having a whole computer built onto one chip. This would lead to an even smaller, more compact, and lower power solution, moving from a multi-component system to a fully self-contained intelligent camera, ready for mass production and widespread deployment.
That's incredible. A closed-loop system, almost like a brain constantly telling the eye how to look, pixel by tiny pixel. Let's dig into the eye itself, the image sensor. How did they design it to be so smart and configurable at that granular level? What's the secret to its architecture that allows for this pixel-wise control?
The image sensor is truly the core innovation here. It's not just any sensor. It's specifically designed for this pixel-wise exposure configurability. The design, outlined in Section 3 and Figure 3 of the paper, was fabricated using a standard 130 nanometer CMOS process. That's a common, cost-effective semiconductor manufacturing method, which is important for integrating it with other electronics down the line. It features an array of 256 by 256 pixels, with each pixel having a very small 6.5 micrometers pitch. That's the tiny size of each individual sensor element. Very compact. And each of these pixels has some key components. There's a standard 4T pixel, which means it uses 4 transistors. This basic building block comprises a pinned photodiode, PD. That's where light is converted into an electrical charge, like a tiny light bucket.
Okay.
Then there's a transfer gate, TX, a reset gate, RST, and a row selection gate, RSEL. You can think of these gates like tiny electronic valves or switches that manage when the light-generated charge is collected, transferred, and reset. But the crucial additions for their pixel-wise control are an exposure control, EX gate, and an in-pixel 1-bit static random access memory SRAM block.
Wait, memory in the pixel itself.
Yes, this SRAM block is a tiny local memory unit that controls the EX gate, allowing it to modulate the exposure for just that specific pixel. So each pixel literally carries its own local memory for its exposure setting right there on the chip.
Wow, okay.
For readout, they utilize a clever technique called analog correlated double sampling, or CDS. That essentially measures and subtracts noise inherent in the sensor, like filtering static from a radio signal to get a clearer sound. They also use cyclic analog to digital converters, or ADCs, for column readout. This was a deliberate choice. Cyclic ADCs occupy less area compared to the successive approximation register, or SAR, ADCs used in some previous designs. Their choice of a single-ended architecture further saves chip space, allowing for that compact pixel pitch and the integration of all those extra gates in memory. Now, what's truly ingenious here is the precise placement of that EX gate. In the previous design, the EX gate was placed between the photodiode, PD, and the transfer gate, TX. This caused a tiny but significant sampling dead time. You can imagine it like a bucket with a very small intermittent leak at the bottom. You're trying to measure all the water collected in the bucket, but some of it is dissipating before you can actually measure it fully. These charges are generated between the end of the previous exposure and the start of the next frame selection, could accumulate in an intermediate node but then be lost when the gates reset. They were simply not included in the final readout.
So you were losing light information.
Exactly, leading to an inaccurate measurement, particularly in dimmer light where every single photon counts. To fix this, in their modified pixel design, as detailed in Figure 5, they cleverly swapped the location of the EX and TX gates. Now, the TX gate is between the PD and the EX gate, and the EX gate is positioned between the TX and the floating diffusion, FD nodes. That's where the charge is converted to voltage. With TX now between PD and EX, the light-generated charges are kept safely at the photodiode, PD, the main bucket, until they are deliberately needed. At the appropriate time, the EX gate is pulled high before the TX gate, creating a potential barrier, imagine a temporary dam. This barrier then protects the charges as the TX pulses transfer them to the intermediate node, preventing them from being reset and lost. These charges are then correctly counted during the final sampling phase. This elegant modification ensures that all light-generated charges are accumulated and measured, effectively plugging that tiny leak in the bucket, making sure every single photon contributes to the final image signal.
So they literally fixed a tiny leak in the bucket, making sure every photon counts. That's a subtle but hugely impactful design change that directly improves the fundamental light capture, especially in low light, as you said. Now, how does this intelligent sensor, this incredibly precise eye, talk to the brain that controls it? You mentioned a high-speed interface. How does that nervous system manage the rapid two-way communication required for real-time adaptation?
Right, that's where the chip-computer bidirectional interface comes in, acting as that nervous system. A high-speed, low-latency interface is absolutely crucial for a rapid feedback loop like this to function effectively. Without it, any significant delays would undermine the real-time adaptation they're striving for. It just wouldn't work. The researchers chose the PCIe bus for this, which, as we mentioned, is a common high-performance interface standard in computers, precisely because of its high bandwidth. It can transfer a lot of data very quickly, and its inherently low transmission latency. For their prototype, they implemented this bidirectional PCIe interface using a Xilinx Kintex 7 FPGA and FPGA being a field programmable gate array, essentially a customizable integrated circuit. They leverage specialized IP cores from Zillabus, which are pre-designed blocks of circuitry for specific functions, to manage the PCIe communication. They carefully characterize the round-trip communication delay for the setup, finding it average around a mere 70 microseconds.
70 microseconds. That's incredibly fast.
It is, with a maximum delay of only 85 microseconds. This speed is absolutely vital because it makes the communication delay practically negligible, especially for typical video frame rates. If you consider anything under 100 frames per second, the time between frames is over 10 milliseconds, or 10,000 microseconds. That 70 to 85 microsecond delay for communication is essentially instantaneous in comparison.
Yeah, loads of time left over.
Loads of time. It leaves the vast majority of the frame interval for the complex control algorithms to run on the computer without causing any instability or noticeable lag in the closed-loop system. They also use the Bonsai visual programming language, with custom plugins, to rapidly prototype and test various feedback control algorithms, showing their commitment to efficient development and experimentation.
That's a super fast data highway, ensuring the eye and the brain are always in perfect sync. Now, for the actual thinking part, the controller. This is where the real intelligence of the system resides, right? The algorithms that decide how each pixel should behave. How does it decide what each individual pixel should do? What algorithms are guiding its decisions to optimize exposure and sampling rate?
Indeed, this is the core of the adaptive intelligence. The pixel-wise exposure and sample rate controller, hosted on that computer for prototyping, has a crucial goal: to optimize each pixel's exposure based on real-time estimates of local light intensity and motion. The aim is to prevent overexposure, underexposure, and motion blur, all happening at the individual pixel level. To achieve this, the controller operates in two distinct yet complementary control modes.
Okay, two modes.
The first is the PI mode, exposure optimization based on intensity. Here, the system uses a proportional integral, or PI, controller for each pixel. To understand PI control, imagine your car's cruise control. A proportional part reacts to the immediate difference between your current speed and your target speed. If you're going too slow, it pushes the pedal more. That's the proportional gain, KP, at work.
Right.
The goal for our pixels is to maintain that pixel's intensity, which they denote as IXY, within a desired target range, specifically just below the point of overexposure. It's always trying to hit a sweet spot for brightness, not too bright, not too dark. The controller calculates an intensity error for each pixel. This error is only considered significant if the pixel's current intensity deviates substantially from the desired target intensity, I-target, beyond a small acceptable error tolerance, ETOL. If it's within that tolerance, the error is considered zero, preventing unnecessary tiny adjustments, kind of like a deadband.
Makes sense.
The PI controller then calculates an output value that adjusts the pixel's exposure. If the pixel is too bright, its exposure is shortened. If it's too dark, its exposure is lengthened. Now, this brings us to a subtle but incredibly important detail: the integral part of the PI controller governed by the integral gain. Many might assume a simple proportional controller, one that only reacts to the current error, is enough. But as the paper clearly shows through a numerical simulation in Figure 6, without that integral gain, a proportional-only controller often leads to a persistent nagging issue called steady-state error.
Steady-state error.
Yeah. Even if the proportional part reduces the error significantly, the necessary rounding of the continuous controller output to a discrete exposure value, because you can't have an infinite number of exposure settings, right?
All right.
That rounding can leave a small, sustained error. The exposure might get close to optimal, but never quite reach it.
So it's like a car's cruise control always being just a tiny bit off, maybe 1 mile per hour under, no matter how much it tries to correct in the moment.
Exactly. That's a great analogy. But with the integral gain in the PI controller, this small, persistent error gets integrated over time. It continuously accumulates that tiny, consistent offness, and this accumulated error then causes the controller to further push the exposure towards the true optimal value, eventually eliminating that steady-state error completely.
So it learns from the consistent error.
Precisely. This means the system won't just react to a flash of light, but will consistently fine-tune itself, preventing any lingering imperfections and achieving a much more precise and stable exposure. It's a system that learns from its own past discrepancies to achieve true stability and precision, a fundamental leap for real-world reliability. The researchers also provide clear rules for selecting the K-app and K parameters, ensuring stability and preventing the exposure from wildly overshooting the target.
That's fascinating. So it's not just reacting to the immediate problem, but also learning from its past performance to fine-tune its precision. That makes it truly intelligent. But light intensity is only half the battle, right? What about motion? How does this system optimize exposure based on movement? That seems like a whole different challenge.
It is. And that brings us to the second mode, the OF mode, exposure optimization based on motion. The goal here is to preemptively tune pixel exposure using optical flow, or OF measurements.
Optical flow, that's tracking movement.
Essentially, yeah. Optical flow tracks how pixels appear to move across frames, giving a sense of motion in the scene. The aim here is to minimize motion blur and also temporal aliasing, where fast motion can look choppy or even go backward sometimes. The ideal scenario for moving objects is to use short exposures and fast frame rates to freeze the motion, much like a very fast shutter speed in photography. However, combining PI and OF modes isn't straightforward, and the researchers identified several challenges. First, if the PI mode is changing exposure, it can cause what they call false optical flow. Even in a perfectly static scene, if a pixel's brightness changes because the PI controller adjusted its exposure, the system might mistakenly detect that change as motion.
Ah, I see. That could confuse things.
It could. Second, optical flow measurements can be inherently noisy, especially in low-light conditions with a low signal-to-noise ratio. It's harder to track things accurately when it's dim or grainy. And third, ironically, long exposures cause motion blur, which then, in turn, degrades the accuracy of the optical flow measurements themselves.
Oh, a vicious cycle.
Exactly. Blur makes it harder to detect motion, which then might lead to keeping longer exposures, which perpetuates the blur. This is where the system demonstrates real intelligence, knowing when to use which mode. It's not just applying a blanket rule, but rather a nuanced decision based on what the scene is actually doing.
So how does it manage that?
To address these issues, they designed a solution where the PI controller and the OF controller engage pixels separately, depending on the magnitude of the pixel motion. The image is divided into subblocks of M pixels, for instance, 8 by 8 blocks in their experiments. The system then calculates the average optical flow for all pixels within each block over a period of time. This spatial averaging across a block, combined with the temporal averaging over a short time window, significantly enhances the accuracy of the optical flow measurement. It helps distinguish real motion from those exposure-induced changes or just random noise.
Smart. Smoothing out the data.
Exactly. Then comes the intelligent switching. If the average motion in a block is below a certain threshold, Vita call PI, the PI mode takes over to control the pixel exposure for that region. It handles static areas or instantaneous motion to get the brightness right. But if the average motion is at or above a different higher threshold, Vita LF, the OF mode takes over for that block. It calculates the exposure based on the magnitude of that motion using a gain factor, KEV, to convert the optical flow magnitude into appropriate exposure steps. So if something is moving very fast within a block, the OF mode will automatically shorten the exposure for those specific pixels and potentially even increase their sampling rate to prevent blur and capture that sharp motion.
So it's like having two highly specialized agents, one for achieving perfect brightness across every pixel, Agent PI, and another for freezing motion, Agent OF, making sure every moving object is crisp and sharp. And the system knows exactly which agent to deploy when, depending on whether it detects significant, persistent movement or just changes in light or brief motion. That's a truly adaptive eye. It's not just passively receiving light, it's actively interpreting the scene and deciding how best to capture it for optimal clarity. It all sounds brilliant on paper. The theory of these two intelligent control modes working together is really compelling, but the proof, as they say, is always in the pudding, or in this case, the pixels. How did the researchers put this system to the test? What kind of experiments did they design to showcase its capabilities and validate its real-world performance against the everyday challenges cameras face?
Right, the validation is key. They designed a robust set of experiments to showcase the system's capabilities, both in static and dynamic scenes, really highlighting the practical advantages over conventional cameras. For their experiments, pixel exposure, XYY, was represented by a 3-bit integer, which means it could take on 8 different values, or steps. The shortest exposure was 30 milliseconds, and the longest was 240 milliseconds, XY equals 8. This configuration allowed for flexible sampling rates from a slowest of about 4 frames per second, FPS, up to a fastest of 30 FPS for individual pixels or regions.
Okay, a decent range.
Yeah, and before any raw images were sent to the controllers, they underwent fixed pattern noise correction and a 3x3 median filter to remove any defective pixel noise, ensuring clean data for processing. Standard pre-processing steps.
Hmm.
For the PI controller, they set the target intensity, iTarget, to 800 with an error tolerance of 120, a proportional gain, KP of 0.01, and an integral gain, key of 0.001 parameters tuned according to their mathematical model for stability, as we discussed.
Yeah.
For optical flow measurements, they use the well-established Fernelbach method, which is a common algorithm for estimating motion in video. They set the optical flow gain factor, KV, to 2, meaning for every 1 pixel of motion magnitude, the exposure was reduced by 2 steps. The spatial averaging for optical flow was done over those 8x8 pixel blocks to enhance accuracy.
Got it.
And importantly, all these operations, including the control algorithms, were processed in real time on a standard PC with an Intel Core i7 processor. The processing time was less than 10 milliseconds, and the PCIe communication delay, as we discussed, was less than 85 microseconds. So truly real-time performance. Their experimental setup, depicted in Figure 7, was quite ingenious. The fabricated 256 by 256 pixel chip was wire bonded onto a PCB and mounted behind an objective lens. Data was then sent via a connector board to a KC705 FPGA, a powerful programmable chip which hosted the PCIe interface and was then connected to the computer running the controller. They devised 2 main types of test scenes. For stationary scenes, they used a back-illuminated cardboard cutout of a cartoon sun with a smiley face overlay. This created a really high dynamic range scenario where some parts were extremely bright and others relatively dark, challenging any camera.
Okay, good test for HDR.
Definitely. For motion scenes, they used objects mounted on a rotating stand, which created continuous motion in the top half of the video frame, while the bottom half conveniently remained stationary for comparison.
Ah, clever. So you can directly compare moving and static areas in the same frame.
Exactly. Very useful for seeing the difference the adaptive control makes.
Let's start with what should be the simpler test, but often isn't for global cameras. Stationary scenes with tricky high-contrast lighting. How did their pixel-wise system handle something like that back-illuminated cutout?
This is where the advantage becomes immediately clear, as vividly shown in Figure 8. When they used a short global exposure of 30 milliseconds, the details like the smiley face and the gaps between the cutouts were visible and easily segmentable, sure, but the entire background was completely dark and underexposed. All information there was lost.
Okay.
Conversely, when they used a long global exposure of 240 milliseconds, the background text, in this case, the MIT logo, became visible, but the bright sun and triangle cutouts were entirely overexposed.
Just white blobs.
Pretty much. The smiley face was saturated into a featureless white blob, and the edges between the shapes shrank, making precise segmentation very difficult for any computer vision system trying to identify those shapes. Now, with their pixel-wise adaptive system operating in PI mode, the controller automatically tuned each pixel's exposure based on its individual intensity. The result in Figure 8C is quite remarkable. The background was intelligently set to a long exposure of 240 meters, ensuring excellent signal-to-noise ratio and clear visibility of the MIT logo. Simultaneously, the pixels within the bright, back-illuminated sun and triangles had their exposures automatically lowered to avoid overexposure. They ranged from 30 meters up to 240 meters in different regions, specifically matched to their local brightness.
Wow, so it balanced it perfectly.
Perfectly. The outcome was that both the background text and the intricate details of the smiley face in the bright region were clearly visible, and the gaps between the circle and triangles were wide and easily distinguishable. It truly captured the entire dynamic range of the scene without compromise, something no single global exposure camera could possibly achieve.
That's a clear and powerful demonstration for stationary scenes, achieving a level of detail across an entire high-contrast image that traditional global exposure simply can't touch. But the true test for any video system, especially for robotics and autonomous vehicles, is motion. How did it perform when things started moving, facing the challenges of blur and rapid changes?
Absolutely. The handling of motion is paramount for these critical applications. They tested 2 scenarios for motion: instantaneous and continuous. First, with instantaneous motion, as shown in Figure 9, they demonstrated the PI controller's responsiveness even when the motion wasn't persistent enough to trigger the dedicated OF mode. In one scenario, they moved the back-illuminated cardboard cutout to the right. During the motion itself, frame 2, pixels in the move region naturally became suboptimally exposed, some overexposed, some underexposed, because their optimal setting changed instantly when the bright object moved over them.
Right, the scene changed under those pixels.
Exactly. The PI controller immediately detected this intensity error and quickly engaged. You can see the pixel exposure starting to regulate in the subsequent frames, frame 3 and 4, and they eventually settled to new optimal values approximately 3 frames after the motion ended, frame 5. This showed how quickly it could correct for sudden changes.
Pretty fast recovery.
Very fast. In another example of instantaneous motion, figure 9b, they moved an incandescent light bulb in front of an MIT logo. Initially, the PI mode optimized exposure, keeping the bright filament of the bulb at a short exposure while maintaining longer exposures for the background logo. When the bulb moved, frames 2 and 3, pixels in the motion region became suboptimally exposed again. And again, the PI controller quickly adjusted, and exposure settled to new optimal values within just a few frames, frame 6. This effectively demonstrates that even for abrupt, non-persistent movements, the PI controller is quickly course-correcting intensity issues on the fly, showing its remarkable resilience and speed.
So even for sudden temporary movements, the system is rapidly adapting the brightness settings on a pixel-by-pixel basis. That's good. But what about continuous motion, where objects are constantly moving and blur is a persistent problem?
Right. That was the more challenging test, the continuous motion scenario, which directly engaged the OF mode, as illustrated in Figure 10. For this, remember, objects were placed on that rotating stand, creating continuous motion in the top half of the frame while the bottom remained stationary. Initially, all pixels were configured for a relatively long exposure of 120 meters, meaning a sample rate of 8 FPS. At these longer exposures, the sampled frames had good signal-to-noise ratio, yes, but the moving top sections suffered from significant blurring effects, clearly evident in frames 1 through 3.
Okay, typical motion blur at slower frame rates.
Exactly. And crucially, due to this blurring, the optical flow measurements in these initial frames were less accurate. They showed a large variance in estimated motion directions, even for objects that were actually moving at a constant speed. This really highlights that blur itself can hinder accurate motion detection, that vicious cycle we talked about for traditional cameras.
Right.
However, as the motion persisted, the optical flow measurements for patches in the moving region were continuously integrated and averaged over time. Once this average motion reached that predefined threshold, the controller intelligently switched from PI mode to OF mode for those specific patches with persistent motion.
Ah, the handoff happened.
The handoff happened exactly where needed. Once the OF mode engaged for frames 4 through 6, pixel exposures were dynamically optimized based on the magnitude of the velocity. The system dramatically shortened pixel exposure for the moving regions, for instance, reducing it down to 30 meters, and simultaneously increased their frame rate up to 30 FPS, all proportional to how fast things were moving according to the optical flow vectors.
And the result?
The result was a remarkable blurless capture of the continuous motion. What's even more impressive is that these blurless frames, captured in OF mode, then led to significantly more accurate motion estimations. The optical flow vectors for the moving pixels now pointed consistently in the same direction, demonstrating that positive feedback loop of intelligence.
That's where the true brilliance of their approach becomes really clear. It's not just fixing the blur in the image. That blur-free image then allows the system to better understand the motion itself, leading to even more precise measurements and the more accurate understanding of the scene. It's a positive feedback loop of intelligence, where better sensing leads to better understanding, which in turn enables even better, more targeted sensing. That's a truly remarkable demonstration of an adaptive system. So we've seen how it works in intricate detail and how it performs in both static and dynamic scenes, clearly outperforming traditional global exposure cameras. But in the world of imaging technology, there are many advanced systems out there, each with its own set of trade-offs. How does this new adaptive pixel-wise system stack up against its predecessors and other advanced imaging technologies in terms of raw performance metrics, like noise, speed, and power?
Right, this raises an important question. What does this all mean for practical performance in a broader context, beyond just these specific experiments? Where does it fit? The paper provides a detailed characterization of their fabricated chip in Table 1, and also a qualitative comparison with several alternative high dynamic range HDR imaging systems in Table 2. This helps highlight its unique advantages and where it sits in the landscape of imaging technology.
Okay, let's break that down.
Let's first look at the chip characterization, Table 1. Their sensor uses an active pixel sensor, or APS, architecture with single-tap readout. This design choice provides significant advantages, allowing them to achieve a better fill factor. Remember, that's the percentage of a pixel's area that is photosensitive and actively collecting light, and a smaller pixel size of 6.5 micrometers. This is often better compared to some previous works that used more complex dual-tap approaches.
More light-sensitive area per pixel, basically.
Exactly. However, there's a trade-off mentioned. It does exhibit higher fixed pattern noise, or FPN. This is a type of noise that appears as a static pattern in the image, often due to variations in manufacturing. They attribute this partly to the specific layout techniques used to maximize fill factor and the fact it's not using a dedicated CMOS image sensor or CIS process, which are usually optimized to minimize FPN.
Okay, so a known trade-off for the better fill factor.
Seems so. Regarding re-noise, Figure 11 shows that it increases with exposure length. This is an expected phenomenon due to dark current leakage current that accumulates even without light, which is contributed partly by the additional floating diffusion node, MID, in their modified pixel design. Still, the noise levels seem quite reasonable overall.
Mm-hmm.
Now, for the qualitative comparison with other HDR systems, Table 2, they pitted their pixel-wise exposure sensor against three other advanced types: address event sensors, AER, logarithmic sensors, and those optical illumination modulation systems we discussed earlier.
Okay, how did they compare?
Well, in terms of simply achieving dynamic range, DR, all four types of sensors can achieve high dynamic range, but their limitations vary significantly. For the pixel-wise exposure sensor, its DR is primarily limited by the shortest exposure time possible, determined by the readout circuitry and photodiode charge transfer. AER sensors, often called neuromorphic or event-based cameras, have DR limited by the max speed of their address event representation transceiver. Logarithmic sensors' DR is limited by transistor biasing conditions, and optical modulation's DR depends heavily on the resolution and accuracy of their SLMs. So they all get HDR, but the how and the limits differ.
What about speed?
When we look at speed, the pixel-wise exposure sensor and logarithmic sensors are broadly comparable due to their use of row select column readout, which is pretty standard. AER sensors, with their asynchronous, event-driven architecture, are generally the fastest as they only report changes in light, not full frames, continuously. Optical modulation systems, constrained by the speed of their SLMs, are typically the slowest for overall video rates. So the Pixel-Y system offers a very good balance of speed for most real-time video applications. Not the absolute fastest, but very capable.
Okay, good balance. Now, what about noise? That seems crucial.
Absolutely. This is truly where the Pixel-Y system shines, and it's a critical differentiator. It's noise and signal-to-noise ratio, SNR performance. The paper argues, and the data suggests, that the Pixel-Y's exposure sensor achieves the best noise and SNR performance among the compared technologies.
The best. Why is that?
Because it benefits from the direct integration of charge within the photodiode, which inherently minimizes what's called shot noise, the fundamental random fluctuations in photon arrival. Furthermore, the use of correlated double sampling, CDS, effectively reduces read noise, as we mentioned. And what's more, a key advantage is its ability to adaptively extend exposure duration for dim regions. When a pixel is in a dark area, it can effectively collect light for longer, which significantly improves its SNR. That's an invaluable capability that fixed frame rate systems simply cannot do.
So it optimizes SNR pixel by pixel too.
Exactly. In contrast, AER and logarithmic sensors tend to suffer from inferior noise SNR, partially due to high fixed pattern noise from process variation and device mismatch, and the inherent difficulty of using time domain CDS effectively. They also often measure photocurrent directly without charge integration, which leads to higher shot noise. Optical modulation systems, while using conventional APS sensors and thus having potentially good noise performance, are hampered by their fixed frame rate, preventing them from adaptively prolonging exposure to boost SNR when needed.
That seems like a huge advantage for the pixel-wise approach then.
It really is, especially for applications needing reliable low-light performance. Finally, considering power consumption, another vital metric for portable or autonomous devices, the pixel-wise exposure sensor boasts the lowest power consumption due to its efficient APS-based pixel architecture. The entire chip consumes a mere 7.31 milliwatts in their test, which is incredibly low.
Yeah, it's tiny.
It is. AER sensors have variable power depending on how active the pixels are, their spiking rate. Logarithmic sensors generally have high power consumption because of constant leakage of subthreshold current, even when not actively capturing. And optical modulation systems also consume significant power due to the additional SLMs they require, which need to be actively driven.
So, if I'm understanding this correctly, you get the best of nearly all worlds with this new system. You get high dynamic range, truly excellent noise performance, and the lowest power consumption, all while being quite speedy for most video applications. That's a powerful combination that fundamentally addresses many of the long-standing compromises in imaging technology. It sounds like a significant step forward, especially for the eyes of autonomous systems that need to be power efficient and highly reliable in diverse conditions. This has been a truly illuminating deep dive into the future of imaging. We've seen how this research moves beyond the inherent limitations of global exposure to a paradigm where every single pixel is a tiny, intelligent camera adapting its vision in real time. We've explored how the ingenious design of the image sensor itself, combined with sophisticated smart control algorithms, is pushing the boundaries of what our digital eyes can perceive, offering incredible clarity and detail in situations that would utterly befuddle traditional cameras.
If we step back and consider the broader implications, this isn't just an incremental improvement to existing camera technology. It feels like a paradigm shift in how we capture and process visual information. We're moving from rigid global settings to a fluid, pixel-level understanding of a scene. And this raises an important question for you, our listener. As cameras become smarter and more adaptable at this most fundamental level, literally learning from what they see, how might this change the way we interact with and rely on computer vision in our daily lives? Think about the capabilities of our phones, the safety of self-driving cars, and what entirely new applications might emerge when machines can truly see without compromise.
Exactly. The possibilities are truly exciting to ponder. What happens when the camera isn't just a dumb sensor anymore? Thank you for joining us on this deep dive. We hope you feel a little more well-informed and perhaps a lot more excited about the incredible technology shaping our world. Until next time, keep digging, keep questioning, and keep exploring.